What if I told you that the fate of Antarctica's climate and a critical piece of our planet's future is being decided by sugar? Not the kind you stir into your tea, but a mysterious, invisible sugar cooked up by microscopic life in the world's most turbulent and remote ocean. For years, our most advanced supercomputers, running incredibly complex climate models, have been consistently failing. They have been stumped by one specific region: the vast, pristine skies over the Southern Ocean. Their predictions just didn't match reality. This is the story of why they were failing, and how a team of international researchers unveiled a secret that connects the microscopic life in the sea to the very clouds that shield our world. This isn't just an academic puzzle. The clouds over the Southern Ocean act as a colossal mirror, reflecting sunlight back into space and cooling our planet. Getting them wrong means our understanding of global warming is incomplete, our future climate projections flawed. Think about it. Every major decision about carbon emissions, every international treaty, every multi-billion-dollar investment in green technology is based on these models. If the models are running with a fundamental error, it's like trying to navigate a ship through a storm with a compass that's off by several critical degrees. We could be underestimating the planet's natural cooling mechanisms, or perhaps misunderstanding how they will react as the world warms. The stakes are immense, and for years, science was missing a key player in this planetary drama. So what was the missing ingredient? What invisible force, hidden in plain sight, was orchestrating the weather at the bottom of the world? In this investigation, we'll dive deep into the ocean's shimmering surface to uncover: how can simple sugars from the sea literally command the skies and seed the clouds? Why was this profound biological link completely overlooked by climate science for so long? And as we explore this breathtaking discovery, we'll ask what it means for the future of our planet in a rapidly changing climate. The answers are more vital than you might imagine. The Southern Ocean is a place of extremes. It's a vast, windswept expanse of water surrounding the icy continent of Antarctica, a world away from the smog and pollution of our industrial continents. Its atmosphere is considered the cleanest on Earth, and that purity is precisely what created the scientific mystery. In most parts of the world, cloud formation, particularly the freezing of water droplets into ice crystals, gets a helping hand from dust. Tiny particles of mineral dust, whipped up from deserts like the Sahara, travel thousands of miles on the wind. These particles act as ice nucleating particles, or INPs. Think of them as microscopic seeds. In a supercooled cloud, where water droplets are below freezing but haven't yet turned to ice, a single dust particle can provide the perfect surface to kickstart the freezing process. Once one crystal forms, it triggers a chain reaction, transforming a water cloud into a mixed-phase cloud of water and ice. This transformation is critical. Icy clouds are brighter, reflecting far more sunlight back into space than pure water clouds. They also behave differently, influencing rainfall and how long the cloud itself will last. Climate models are built on this principle. Dust makes ice. But in the southern hemisphere, this logic breaks down. There are no major deserts. The vast landmasses of Australia, South America, and Africa are too far away to consistently supply the skies over the deep Southern Ocean with dust. Yet satellites and on-the-ground measurements showed that ice was indeed forming in those clouds, far more than the minuscule amounts of dust could account for. The models, programmed to rely on dust, kept predicting watery, less reflective clouds, while reality showed something much icier and brighter. The numbers simply didn't add up. The models were broken. This wasn't just a small rounding error. The discrepancy was huge, a gaping hole in our knowledge. It was a scientific ghost haunting the world's climate scientists. They tried everything. Was it some unknown atmospheric chemistry? A strange interaction with the ozone hole? Was there a long-range transport of dust from a source no one had considered? Hypotheses were proposed and systematically shot down. The evidence stubbornly pointed back to the ocean, to a biological source, but the trail always went cold. It was a classic locked room mystery, but the room was the size of an ocean, and the culprit was invisible to the naked eye. For over a decade, scientists have known that the ocean itself could be a source of these ice-seeding particles. The churning, frothing surface of the sea creates sea spray, tiny aerosol droplets that are launched into the atmosphere. They knew that something biological within that spray had the ability to nucleate ice, but the exact chemical identity of this potent, ocean-borne ice maker remained a ghost. The trail went cold until a crucial clue emerged from the opposite pole. During an expedition to the Arctic in 2017, researchers noticed unusually high concentrations of glucose in their samples. Glucose, a simple sugar, is a building block of larger, more complex sugar molecules known as polysaccharides. Dr. Sebastian Zeppenfeld from the Leibniz Institute for Tropospheric Research, or TROPOS, had a hunch. He recalled, "It was therefore obvious to us that polysaccharides could be the missing piece of the puzzle." Could these complex sugars, produced by life in the ocean, be the mysterious ice-seeding agent that science had been hunting for? This hypothesis sparked a major international effort, bringing together experts in aerosol microphysics, atmospheric chemistry, and global modeling. The investigation turned its focus to the very skin of the ocean, the surface microlayer. This is not just water. It's a vibrant, bustling ecosystem, a cosmos of microorganisms. It's teeming with bacteria, algae, marine diatoms, viruses, and, crucially, marine fungi and protists. Let's pause and visualize this world. This surface layer, thinner than a human hair, is one of the most biologically active places on Earth. It's a shimmering, gelatinous film, a soup of life. Here, single-celled algae, the powerhouses of the ocean, are photosynthesizing, creating energy from sunlight. Bacteria are furiously at work, decomposing organic matter. And among them are the fungi and protists, the unsung heroes of our story. They are nature's great recyclers, but in their daily business of living and dying, they shed these complex polysaccharide molecules. These molecules are not just waste, they are incredibly sophisticated structures, chains of sugar woven into specific shapes that, by a remarkable quirk of evolution, happen to be perfectly shaped to trick water into freezing. The theory was simple yet elegant. As waves break and bubbles burst, these powerful polysaccharide molecules are ejected into the air within sea spray. They rise into the atmosphere, journeying into the cold upper layers where clouds form. There, they perform their magic. And what is this magic? It's a masterpiece of molecular deception. Supercooled water is in a fragile, unstable state. It wants to freeze, but it needs a template, a molecular blueprint to follow. The specific atomic arrangement of these polysaccharide chains mimics the crystal structure of ice. When a polysaccharide aerosol encounters a water droplet, it offers that blueprint. The water molecules snap into alignment and a tiny ice embryo is born. This single event unleashes a cascade. The new ice crystal begins to grow rapidly, pulling water vapor from the surrounding liquid droplets in a process of molecular theft. This makes it grow hundreds of times larger than its neighbors, dramatically altering the cloud's composition and, most importantly, its brightness. To prove this, Dr. Susan Hartman at Tropos conducted a series of meticulous laboratory experiments. Using a specialized setup called the INDA, or Ice Nucleation Droplet Array, they tested the ice-forming ability of polysaccharides derived directly from marine fungi and protists. They placed microscopic droplets containing these sugars onto a cold plate, slowly lowering the temperature and watching carefully to see when they would freeze. The results were astounding. The data showed that these marine polysaccharides were incredibly effective ice nucleators. They consistently triggered freezing at temperatures between -15 and -20 degrees Celsius. This wasn't just a minor effect, it was a powerful, reliable mechanism. The lab work proved that the sugars could be the culprit. But was it happening on a global scale? Was this enough to explain the discrepancy in the climate models over the entire Southern Ocean? Isn't it just incredible to think that the microscopic life in the sea could be having such a massive impact on the sky above? If you find this connection between the ocean and the atmosphere fascinating, do us a favor and hit that like button to let us know. It really helps us bring more stories like this to you. To answer the question of global significance, the team turned to the digital world. Dr. Roland Schrodner, also from Tropos, fed the new data into a powerful global atmospheric chemistry transport model called TM5. This model simulates the movement of particles and chemicals all around the globe. When they plugged in the ice nucleating properties of the polysaccharides, the simulation suddenly clicked into place. Dr. Schrodner summarized the groundbreaking findings. In our simulations, we were able to show that at -15 to -16 degrees Celsius, the polysaccharides over the gigantic areas of the oceans in the clean southern hemisphere are probably the most important ice nuclei, more important than mineral dust. In that critical temperature range, where most of the sun-reflecting mixed-phase clouds exist, it's not dust from distant deserts that's calling the shots, it's sugar from the ocean. This discovery fundamentally rewrites our understanding of cloud formation in remote marine environments. It paints a new, more complete picture. In warmer clouds, just below freezing, proteins from bacteria are likely the main biological ice starters. In the very coldest clouds, below -20 degrees Celsius, the few mineral dust particles that do make it that far can still play a role. But in that vast and crucial middle ground, from roughly -10 to -20 degrees, where the reflective properties of clouds are so sensitive, polysaccharides are the dominant force. This is a paradigm shift. For decades, climate models have been built with a geological bias, assuming that the main drivers of ice formation were inert particles of dust and soot. This research proves that in the planet's cleanest regions, the biosphere is in control. The living, breathing ocean is directly linked to the physical state of the atmosphere above it, in a beautifully complex feedback loop that we are only just beginning to understand. The implications are profound. As nations around the world work to reduce man-made pollution and aerosol emissions, our atmosphere will, in many places, begin to resemble the clean air of the southern hemisphere. This means that natural aerosols, like these marine sugars, will play an increasingly important role in shaping our planet's clouds and climate. Understanding their function is no longer a niche interest. It is essential for accurately predicting our climate future. The story is far from over. This discovery has opened up a whole new avenue of research, and scientists are gearing up for major expeditions to unlock the remaining secrets of the southern clouds. From July to October of 2025, the German research aircraft HALO will fly the HALO South mission. This flying laboratory will soar through the clouds over the Southern Ocean near New Zealand, armed with state-of-the-art instruments to measure the intricate dance between aerosols, clouds, and radiation in unprecedented detail. The HALO aircraft is packed with lasers, spectrometers, and particle counters that can analyze individual aerosol particles and cloud droplets in real time as the plane flies right through them. It will be able to sniff out the chemical signature of these sugars directly in the clouds where they are active. Simultaneously, on the ground, the Go South 2 campaign will deploy a mobile cloud observatory known as La Crosse at the southern tip of New Zealand. From September 2025 all the way to March 2027, this station will stare into the sky, providing a continuous, long-term record of the clouds rolling in from the world's wildest ocean. This dual approach is vital. The aircraft provides a detailed, high-resolution snapshot, while the ground station provides the long-term context, observing how the clouds evolve through different seasons and weather patterns. Together, they will create a four-dimensional movie of the southern clouds, finally revealing the full story of the ocean's influence. The Leipzig-based researchers hope that this combined effort from both the air and the ground will finally tame the mysteries that have for so long been hidden within the clouds of the less polluted southern hemisphere. We are standing on the cusp of a new understanding, where the boundaries between biology, chemistry, and meteorology are blurring. We'll be keeping a very close eye on the results from these missions as they come in. To make sure you don't miss our future updates on these groundbreaking discoveries, take a moment to subscribe to our channel and turn on notifications. So the next time you look at the ocean, don't just see a vast expanse of water. See a living, breathing chemical factory, an ecosystem that is actively shaping our weather and climate. one microscopic sugar molecule at a time. The failure of our climate models wasn't a flaw in their programming, it was a gap in our knowledge, a humbling reminder that the Earth system is more interconnected and biologically driven than we ever imagined. The sweet secret of the southern clouds has been revealed, and it's a testament to the powerful, hidden forces of the natural world. What other secrets does the deep ocean hold? We are only just beginning to find out.